All right, welcome. Today we're going to demystify one of the biggest, most important ideas in all of computer science, data structures. They're kind of the secret sauce behind, well, pretty much every app and website you use. So let's pull back the curtain and see how it all works. Okay, so let's start with a thought experiment. Imagine you have 1,000 books, just, dumped in a giant pile in a room. How in the world would you find one specific book in, say, under a minute? It'd be a total nightmare, right? Of course, you'd come up with a system. You'd sort them by author or maybe by genre. You'd create some kind of catalog. Well, that exact problem, that's what programmers deal with all the time. But instead of books, they're organizing data. And that's it. That is the core idea. Creating a smart, efficient system to organize stuff so you can find it later. That's exactly what a data structure is in the world of programming. Think of it like the blueprint for how all your data is going to be stored and handled. So to put it simply, a data structure is just a particular way of organizing data so a computer can work with it effectively. It's not just one thing, like a single filing cabinet. No, it's more like the entire system of a library. You've got the shelves, the catalog, the checkout process, the whole shebang. So why do we even care about this? I mean, why is it so important? Well, it all comes down to two things: speed and memory. Performance. If you pick the right data structure for the job, your program will be lightning fast and won't hog all the computer's memory. It's literally the difference between an app that feels snappy and one that, just feels clunky and slow. Okay, let's get into it. We're going to open up the programmer's basic toolbox and look at the simplest types first: linear structures. And the name says it all, really. These are just ways of organizing data where everything is lined up one after another in a sequence. First up, we have something called a stack. And just look at this picture. It's literally a stack of vans, and that is the perfect way to understand how this thing works. See, a stack follows one super simple rule: last in, first out. We call that LIFO for short. Just imagine you're washing dishes and you're stacking plates. The last plate you put on top of the stack is going to be the very first one you grab when you put them away, right? You're not going to try and pull one from the bottom unless you want a mess. Now, what's the opposite of a stack? Well, that would be a queue. This one works on a first in, first out principle, or FIFO. And this is something you see every day. Think about standing in line at a grocery store. The first person who gets in line is the first person to check out. It's simple, it's fair, it's orderly. So let's just nail this down because it's the most important part. LIFO for a stack, you're always dealing with the newest thing you added. FIFO for a queue, you're always dealing with the oldest thing. And that one little difference completely changes how and when you'd use them. It has huge implications in programming. All right, moving on. Let's talk about two of the most fundamental, most common building blocks you'll find anywhere in programming: arrays and linked lists. Okay, so what's an array? The best way to think of it is like houses on a street. They're all lined up right next to each other, in order, in one big block of memory. House 1, house 2, house 3, you get the picture. A linked list? Totally different. It's more like a scavenger hunt. Each item has two things: the piece of data itself and a clue, we call it a pointer, that tells you exactly where in the computer's memory to find the next item in the list. It could be anywhere. And this structure, this little package of data and a pointer, we call it a node. And it makes linked lists super, super flexible. Let's say you want to add a new house in the middle of our street. With an array, that's a huge pain. You might have to move everything down. But with a linked list, easy. You just change a couple of those pointer clues. It's way less destructive. But let's be real, life isn't always a straight line, right? And neither is data. What if you need to represent something with way more complex connections, like a family tree or a map of every road in a city? For that, we gotta break out of the line and go non-linear. And that brings us to these two, trees and graphs. A tree, like you see here, is all about hierarchy. You start with a single root at the top. Think of it like the CEO of a company. And it branches down into child nodes, which can have their own children. But a graph is a totally different beast. It's just a web of connections. Any point or node can connect to any other node. It's perfect for things that are all interconnected, like, say, your friends on a social network. So you're probably seeing the big trade-off here. Linear structures, they're simple. They're easy to get your head around, easy to go through from start to finish. Nonlinear ones, though, they are definitely more complex to set up and get around in. But, and this is a big but, they are way more powerful for modeling how things work in the real world, and they can actually be much smarter about how they use memory. Okay, so we've got all these different filing systems, right? All these clever ways to store our data. But how do we actually do stuff with it? How do we find something or sort the whole list or add a new piece of information? Well, to answer that, we have to talk about a really important difference. And here is the absolute simplest, most powerful way to remember this. Data structures are the nouns. They're the things, the objects, the containers. Algorithms are the verbs. They're the action words. They're the instructions that tell you what to do with the nouns. So let's break that down. A data structure, your array, your tree, whatever, it's just the framework. It's the filing cabinet. An algorithm, like a search or a sort, is the set of steps you follow to use that filing cabinet. You see? You can't really have one without the other. They're a team. They work together to make great software. Now, you might be thinking, okay, this is some interesting computer science theory, but why does it matter to me? Well, the truth is you are using these ideas, these data structures, literally all day, every day, even if you don't know it. No, seriously, think about it. You open up a social media app, your network of friends is a giant graph. You use your GPS to get somewhere? That's a powerful algorithm running on a graph of all the roads. You know the back button on your web browser? That's a stack. It just pops the last page you visited off the top. Even the folders on your computer, that's a tree structure. And when you send a bunch of documents to the printer? Yup, that's a queue. And this quote just nails it. Every feature, the speed, the magic of the technology we rely on, it all comes down to a developer somewhere making a really smart choice about which data structure to use for the job. It's all about that behind-the-scenes organization. So I'll leave you with this question. The next time you use an app and it just works, instantly, take a second to think about what's going on under the hood. Which data structure are you gonna think? Because these aren't just abstract ideas for coders. They are the invisible architecture, the skeleton holding up our entire digital world. When it comes to technology, good organization isn't just important, it's everything.